Continuity. A function f is continuous at a number a if the limit of f of x as x approaches a is equal to the function value at a. You should notice that this definition requires three things to be true. Number one, the function value at a must be defined. That means that the number a needs to be in the domain of your function. The limit as x approaches a of f of x must exist, and those two values must be equal to each other. So if you look at the graph below here, for this particular function, we can see that it is continuous at a because number one, f of a is defined. It's this point right here, which corresponds to this value on the y-axis. Also, if we take the limit as x approaches a from either side, we can see that it is approaching that number as well. So f of a is this number. The limit as x approaches a is this number. So they are the same, and therefore the function is continuous here. What this means from an intuitive perspective is that a function is continuous at a point if you can continuously draw that function without lifting your pencil off the paper. Let's take a look at an example of a function that is not continuous at a number. Look to the other graph. We can see, for example, here at x equals 1, the function is not continuous. Now, why is that? Well, if you look at 1, the function has a hole at that number. And what that means is f of 1 is not defined. And if a function value is not defined at a particular number, then it cannot be continuous at that number. Now look at x equals 5. F of 5 is defined. It's equal to this value up here. However, if you take the limit as x approaches 5, the function values are getting closer to this number, not this number. So even though the limit is defined and the function is defined, they are not the same, and therefore the function is not continuous at 5. Also, the function is not continuous at 3, and this is probably the most obvious, because if I'm graphing this function, clearly I have to lift my pencil off the paper to come up here to continue graphing this function. But let's go through it. F of 3 is defined. It is this number down here. But the limit as we approach 3 from the left-hand side is this number, and the limit as we approach 3 from the right-hand side is this number. So the left limit and the right limit are different, and that means the overall limit does not exist, and that violates the fact that the limit must exist. So as soon as the limit doesn't exist, we know it cannot be continuous. If the function value does not exist, we know it cannot be continuous. And if both of those things do exist, they have to be equal in order for the function to be continuous at that number. Now let's take a look at some examples where we don't have the graph. So for the first function here, we want to know where are each of the functions discontinuous. So if you look at this function here, clearly you cannot plug in x equals 2. So we know that f of 2 is not defined. Since f of 2 is not defined, this means that f of x is not continuous at x equals 2. And we're going to use the abbreviation CTS to mean continuous. In the next function, you can see that f of x is defined for all values of x. Basically, this function is the same as this one. So if x is not equal to 2, we use this function. If x equals 2, we say that f of 2 is equal to 1. So for that function, f of 2 is defined. It is equal to 1. But now we need to check what is the limit as x approaches 2 of f of x. Well, when you're approaching 2, you're not equal to 2. So as x approaches 2, we have to use this definition for the function. And so this will be the limit as x approaches 2 of x squared minus x minus 2 divided by x minus 2. Now, if you plug in 2, you are going to get 0 divided by 0. So let's go ahead and see if we can algebraically simplify this, and of course we can. The numerator will factor into x minus 2 times x plus 1. And once we do that, you can see that the x minus 2 factor cancels out, and we get the limit as x approaches 2 of x plus 1. And now, because that is basically a polynomial, we can simply plug in 2 and get 2 plus 1, which is equal to 3. So the limit is equal to 3, so it exists, but the function value is equal to 1. And in order to be continuous, the function value and the limit have to be the same thing. So f of 2 is equal to 1, and that is not the same as the limit as x approaches 2 of f of x, because that was equal to 3. Therefore, the function is not continuous at x equals 2. And for the third example there, clearly we can see that we seem to have a problem when x equals 0, because if you're talking about the function 1 over x squared, we know that x cannot be 0 here. But they'd have to find f of x to be 1 when x is 0. So, once again, we know that f of 0 exists. It is equal to 1. However, if I take the limit as x approaches 0 of f of x, this will be the limit as x approaches 0 of 1 over x squared. And if you remember what happens here, when you plug in small numbers for x here and you square them, you will still get small numbers, and they will always be small positive numbers. And this is because no matter if you're plugging in negative numbers or positive numbers as you approach 0, when you square them, they become positive. And so 1 divided by small positive numbers gives you a large positive number. And technically, since the limit is infinity, that means that this limit does not exist. And as soon as your limit does not exist, we can say this function is therefore not continuous at that value of x. And that value, of course, is x equals 0. So all three of these functions have an issue with continuity at various numbers, according to the definition. Now, I thought I would bring in the graphs of these functions just to show you what's happening here. So in the first example here, the graph looks like this. So it just has a hole in the graph at x equals 2, and that is why it was not continuous at x equals 2. And this is called a removable discontinuity, because all we've done is we've removed a point from the graph. The second function looks just like the first function, except that we have defined f of x to be 1 when x equals 2. So when x equals 2, we can see we have the point 1 here. However, it's still discontinuous at 2 because we have still removed a point from the graph. And so both of these are examples of what's called a removable discontinuity. In the third function, you can see that as x gets closer to 0, the function is going to infinity. And so even though f of 0 is equal to 1, the limit does not exist, and therefore we have a discontinuity there. And this is called an infinite discontinuity because we have an asymptote here, and the function is going to infinity there. And the fourth graph is something that I didn't go over algebraically, but when you have a function that jumps from one section of the graph up to another section, clearly these are discontinuities, and these are called jump discontinuities. So these are the various types of discontinuities you can have: removable, jump, and infinite discontinuities. A function is continuous from the right at a number a if the limit as x approaches a from the right is equal to the function value at a, and it's continuous from the left at a if the limit from the left at a is equal to the function value at a. So I thought I would just provide a graphical example here, and I'd like to show you that at the number x equals 3, the function here, f of x, is continuous from the left. Now, why is that? Well, as x approaches 3 from the left, you can see the function values are getting closer to this value. And that is the function value. In other words, f of 3 is equal to this number. And the limit is also approaching that same number. So we can see from the graph that if you take the limit as x approaches 3 from the left of your function, that this is actually equal to f of 3. And that is why it is continuous from the left. However, at x equals 3, f of x is not continuous from the right. Now, why is that? Well, just look at the graph. As we approach 3 from the right, the function values are approaching this number. So the limit is this value up here. However, the function value at 3 is still down here. So what we have here is the fact that the limit as x approaches 3 from the right of your function is not the same as f of 3. So this would be an example of continuous from the left and not continuous from the right. Now, of course, we could alter the graph, right? I could fill in this point, and down here I could turn this into an open circle, and now those circumstances would be reversed. If this were the case, now it would be continuous from the right at 3, and it would be discontinuous from the left. And as a final note here, please notice that I cannot do this, right? I cannot fill in both points, because if I do that, then it's no longer a function, because f of 3 can only be one value. It cannot be two different values. So this is the concept of continuity from the left and from the right. A function f is continuous on an interval if it is continuous at every number in the interval. If the function is defined only on one side of an endpoint, we understand continuous to mean continuous from the left or continuous from the right as appropriate. So for example, consider this function here, and here is the graph of this function. So this function is only defined on an interval from x equals -1 to x equals +1. And we can see clearly this function is continuous because I can graph this function starting here all the way over to the other side without lifting my pencil off the paper. So this function is continuous on that interval. Now, at the endpoints, so at this endpoint right here, we would say it is only continuous from the right, because as you move to that point, on the function, you can only move toward this point from the right-hand side of -1. And at the other endpoint, we would say it's continuous here, but only from the left. Because if you're on this function moving toward that point, you can only be moving toward x equals 1 from the left-hand side. So we understand this is a continuous function, but at the endpoints, it's only continuous from the side where the function is defined. Now we have some really intuitive and basic theorems, but these theorems are extremely important. The first theorem says if f and g are continuous functions at a and c is a constant, then when you add those two functions, subtract those two functions, multiply a function by a constant, multiply two functions together, or divide two functions, all those functions are continuous as well. So when you add, subtract, multiply, or divide functions, or multiply a function by a number, if those functions were continuous in the first place, then all the resulting functions are continuous as well. The other theorem says any polynomial is continuous everywhere, and rational functions are continuous wherever it is defined. So for example, down below here, find the limit as x approaches -2 of this function. Please note that this is a rational function. And so if I wrote down f of x is equal to x cubed plus 2x squared minus 1 over 5 minus 3x, the domain of this function is 5 minus 3x cannot be 0, right? The only issue you get from a rational function is if you divide by 0. So if 5 minus 3x is equal to 0, then 5 would have to be equal to 3x, and that would mean that x would be 5 divided by 3. So that can't be true. Okay, so the domain of this function is all numbers from -infinity up to 5/3 union all the numbers from 5/3 up to infinity. So this is the domain. So this theorem says that this rational function is continuous wherever it is defined. So it is continuous for every number except 5/3. So if I want to take the limit as x approaches -2, -2 is not 5/3. So we know this function is continuous at -2. And therefore, we know that it will equal the function value at -2. So all this is to say that if I want to compute a limit of a rational function, as long as I'm not dividing by 0 at this number, all I have to do is plug this number in. So the limit here is going to be -2 to the 3rd power plus 2 times -2 squared minus 1 divided by 5 minus 3 times -2. And if you do the math, you get -8 plus 8 minus 1 divided by 5 plus 6, and this is -1 over 11. The following types of functions are continuous at every number in their domains. Polynomials, we just mentioned this in a previous theorem. Rational functions, also just mentioned that, but also root functions, trigonometric functions, inverse trigonometric functions, exponential functions, and logarithmic functions. In other words, all of the functions that we ever talk about are continuous at every number in their domain. So as an example, we ask, where is the following function continuous? And notice that this is a really complicated function. F of x is the natural log of x plus the inverse tangent of x, all divided by x squared minus 1. Well, the answer is this function will be continuous at every number in its domain. So we have to take this piece by piece. So let's consider the natural log of x. The domain for the natural log of x is all numbers from 0 to infinity. In other words, you cannot plug a negative number into a natural log, and you also cannot plug 0 into a natural log. So since natural log is restricted to this domain, this function would also be restricted to that same domain, right? Because even though we can plug negative numbers into here, we cannot plug a negative number into a natural log. Now, how about inverse tangent? What's the domain of inverse tangent? Do we have any further restrictions? Well, the answer is no. The domain of inverse tangent is minus infinity to infinity, and this is because the graph of inverse tangent looks like this. Okay, and this is just a rough sketch of the graph, but we can see that the domain is all real numbers. Now, x squared minus 1, it has a domain which is also all real numbers. We can plug in any number we want into x squared minus 1. However, because x squared minus 1 is in the denominator of a fraction, we know that x squared minus 1 cannot be equal to 0. So how would x squared minus 1 be equal to 0? Well, you can do this a couple of different ways. The easiest way to do it would be to add 1 to both sides, and then you could take the square root of both sides, and this would give you x equals plus or minus 1. So positive 1 and negative 1 would both be restricted values from this domain, because if you plug in 1 or negative 1 here, you will be dividing by 0. So where is this function continuous? It's continuous on its domain. And what is its domain? Well, let's review. We've already said that we have to restrict the domain to be only numbers from 0 to infinity. So that would be numbers that look like this. However, we have an additional couple of restrictions here. X cannot be negative 1, which is not a problem because negative 1 is over here, and that's already restricted from consideration. But also x cannot be positive 1. And so we have to restrict that value as well. So the domain of this function is all numbers from 0 to 1, union all numbers from 1 to infinity. And since that is its domain, that is also going to be the interval on which this function is continuous. Because this function is made up of log functions, inverse trig functions, polynomials, and then we're adding those functions together and then dividing by this function. And we know that this function will be continuous at all the places where these functions are continuous, as long as we're not dividing by 0. If f is continuous at b, and if the limit as x approaches a of g of x is equal to b, then the limit as x approaches a of f of g of x will be equal to f of b. So in other words, what we're saying here is if you have the limit of the composition of two functions, you can move this limit inside of this composition. And the next theorem says if g is continuous at a and f is continuous at g of a, then the composite function f of g is also continuous at a. And we can use these theorems to help us do limits like the following. Evaluate the limit as x approaches 1 of the arcsine of 1 minus radical x over 1 minus x. So when I go to take this limit, first thing you need to realize is that you have a composition here. You have the arcsine of another function. So the theorems previously mentioned allow us to move this limit inside the arcsine. So this becomes equal to the arcsine of the limit as x approaches 1 of 1 minus radical x over 1 minus x. Now we just have to focus on doing this limit. We can ignore the arc sign temporarily. But notice that if you were to try to plug in 1, you would be dividing by 0. And on top, you would also get 0. So this limit ends up being 0 divided by 0, which means we need to work on this expression. So let's take 1 minus radical x divided by 1 minus x, and let's multiply it by the conjugate 1 plus radical x, top and bottom. And let's see what this gives us. So on top, when we multiply these together, we get 1 times 1, which is 1. 1 times radical x is plus radical x. 1 times negative radical x is negative radical x. And negative radical x times positive radical x is negative x. And in the denominator, let's not multiply these out. Okay, so when you multiply by a conjugate, the important thing is that you only multiply the conjugates together. The things that are not conjugates, leave them in factored form. And notice what happens to the numerator. The positive radical x and negative radical x cancel. And this becomes 1 minus x on top over 1 minus x times 1 plus radical x. So this is equal to 1 minus x over 1 minus x, 1 plus radical x, and then we have the good fortune here of being able to cancel those out. And don't forget there's still a 1 on top. And now we can rewrite this limit as the arc sine of the limit as x approaches 1 of 1 over 1 plus the square root of x. And now to finish this, we can simply plug in 1 here, right? Because this is a continuous function, so we can plug 1 in. And so we are going to get the arc sine of 1 over 1 plus the square root of 1, which is the arc sine of 1 over 2, 1/2. And then now we have to figure out what is the arc sine of 1/2. Well, it turns out that it's pi over 6. Okay, you know this from trigonometry. If you don't know this, then the way you figure this out is you draw a triangle, and we're going to label this angle theta. And we know that the sine of theta is equal to 1/2. So that means sine is opposite over hypotenuse. You can solve for the missing side here, which ends up being radical 3. And you should recognize this as a 30, 60, 90 triangle. So in other words, we know that this theta down here is 30 degrees. And 30 degrees is the same as pi over 6 radians. Okay? You can also get this value from knowing the unit circle. But I personally like to draw these triangles to remind us of these special triangles, which turn out to be really important. Next example, for what value of the constant c is the function f continuous on minus infinity to infinity? I want you to notice that the function is defined piecewise. It is equal to this function here if x is less than 2, and this function here if x is greater than 2. Both of these are polynomial functions. So what we need in order for this to be continuous is we need the limit as x approaches 2 from the left of f of x to be equal to the limit as x approaches 2 from the right of f of x. So let's go ahead and calculate the limit as x approaches 2 from the left. If we're approaching 2 from the left, we are less than 2, which means we'll be using this function. So we have the limit as x approaches 2 from the left, cx squared plus 2x. And because this is a polynomial, we can basically just plug 2 in. So we get c times 2 squared plus 2 times 2. This is 4c plus 4. Okay, now we'll hang on to this for a minute. And now let's go ahead and compute the limit as x approaches 2 from the right. Now, if you're approaching 2 from the right, that means you would have to be greater than 2. So we're going to use this function now. So limit x approaches 2 from the right, we have x cubed minus cx. Again, we know this is a polynomial, so to evaluate this limit, we can simply plug in 2, and that gives us 2 cubed minus c times 2, which is 8. I said minus, excuse me. So this is 8 minus 2c. Okay? Now, in order for this function to be continuous, this left limit and this right limit must be equal to each other. So 4c plus 4 must be equal to 8 minus 2c. And now we just solve for c. So I'm going to add 2c to both sides. I'm going to subtract 4 from both sides, and then divide by 6, and we get c must be equal to 2/3. So in order for this to be a continuous function, c would have to be 2/3. Lastly, we have the intermediate value theorem. Suppose that f is continuous on the closed interval ab. Let n be any number between f of a and f of b, and f of a and f of b have to be different. If this is true, then there must exist a number c in between a and b such that f of c is equal to n. So let's just think of this in the context of a graph. So here I have a continuous function, f of x. So I can draw this function without lifting my pencil off the paper. And I want you to notice that f of a is this value, and f of b is this value up here. So f of b and f of a are not equal to each other. They're clearly different values. If you pick some number n between a and b, then there must be a number c. Excuse me, I believe I said that wrong. If you pick a number n between f of a and f of b, then there must be a number c corresponding to that such that f of c is equal to n, and c has to be a number between a and b. This is because if the function is continuous, when you go across here, you are going to hit that function eventually, and there will always be a number c that corresponds to that number n. In fact, there might be multiple numbers that satisfy it. So here we have the same scenario, a continuous function. F of a and f of b are different. I pick a number n in between f of a and f of b, and notice now that there are 3 values that correspond to that number n. This is what we call the intermediate value theorem, and it's true because the function is continuous. So because when I graph this function, I can't lift my pencil off the paper, it is assured that if I pick a number here, when I draw across, I am going to hit that function at least once, meaning that there will be at least one value of c corresponding there. Let's do an example using this theorem. So here we want to use the intermediate value theorem to show that there is a solution of the given equation on the specified interval. Okay, so first of all, let's take this equation here and let's play around with it just a little bit. So we have the natural log of x is equal to x minus the square root of x. If I move these terms to the left side, this equation becomes the natural log of x minus x plus the square root of x is equal to 0. Okay? Now, let's say that f of x is this function. How do I prove that f of x would have to equal 0 in between 2 and 3? Let's think about that for just a minute. So if you have a function and it's equal to 0, you know that means that's the point where it crosses the x-axis, right? So at this point right here is where f of x is equal to 0. The way that we can ensure that this happens is that if we pick a number to the left and a number to the right, so call this A and call this B, I want you to notice that f of A is negative and f of B is positive. If f of A is positive or negative and f of B is the opposite of that, then that means that one of these points is below the x-axis and the other one is above. And if the function is continuous, the intermediate value theorem guarantees that we have to cross the x-axis somewhere in between A and B. So all I have to do to show that we're guaranteed to have a solution to this equation is just show that this function is positive or negative at 2 and is the opposite of that at 3. So what is f of 2? F of 2 is the natural log of 2 minus 2 plus the square root of 2. And we can actually use a calculator to help us with this. So we can see from the calculations here that this number is equal to 0.107 approximately. And f of 3, which would be the natural log of 3 minus 3 plus the square root of 3, ends up being approximately negative 0.169. So we can see that f of 2 is positive, f of 3 is negative. So in terms of the graph of the function, what this means, since f of 2 is positive, it's above the x-axis. Since f of 3 is negative, it's below the x-axis. And since the function is continuous, we are guaranteed that the function has to cross the x-axis somewhere in between 2 and 3. That means we are guaranteed that the function must be equal to 0 somewhere in between 2 and 3. So that means that the original equation must have a solution somewhere between 2 and 3. And this concludes this lesson.